hello. Let's just dive right into Chapter 2 notes. This chapter should be a review of Chem 1. We're going to briefly talk about what makes an element, the parts of an atom, how molecules and compounds form. We're going to talk about the properties of water and what makes water so unique, and discuss acids and bases and talk about where they're found in the body and what makes them different from each other. So to just dive right in with section 1, matter refers to anything that has mass and occupies space. It exists in 4 different states: solid, liquid, gas, and plasma. So the 3 first ones we have here on Earth at all times. Plasma is created when lightning strikes and in space. All matter, both living and non-living matter, is composed of basic substances called elements. Elements are substances that cannot be broken down any further and retain their properties. They're composed of an atom. There are 92 naturally occurring elements. You can find those on the periodic table. 6 of them make up 95% of our body weight. There's an acronym, CHNOPS, to help you remember which ones they are. They are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. So here we have a chart that shows us in blue the percentage of Earth's crust that is made up of different elements compared to organisms, to living things. So you'll notice that living things have a lot of oxygen, a lot of nitrogen, a lot of carbon, a lot of hydrogen, and then we have trace amounts of these metals over here. Atoms are the smallest part of any element that can display the properties of that element. They're made up of protons, neutrons, and electrons. Found in the nucleus are protons, which are positively charged, and neutrons, which have no charge at all. And outside of that central nucleus are electrons, which are negatively charged, and they are extremely small. And so we just kind of ignore them whenever we do calculations because they're so stinking small that it won't affect our numbers at all. Here's the general structure of an atom. Protons and neutrons are in the nucleus in this central region right here, and electrons are found in this outer area here, often called an electron shell. You'll notice how much smaller they are. This isn't even to scale. Okay, this is way bigger than an electron actually is compared to a proton or a neutron. Atomic number and mass number. Each element is represented by 1 or 2 letters that give it its unique atomic symbol. So if you have a capital H alone, that will always represent hydrogen. If you have He, that will always represent helium. If you have P, that equals sulfur. Okay, each element has its own atomic symbol. The atomic number is equal to the number of protons in that element, and if the atom is neutral, it's also the number of electrons. The mass number is the number of protons plus the number of neutrons that are found in the nucleus. And the atomic mass is approximately equal to the mass number that you can find on the periodic table. Here we have our atomic symbol with our mass number and our atomic number. This gives you all the information you need to know about an atom with these things. It tells us what element it is, its atomic number, its mass number. We can figure out how many neutrons it has from this, and how many protons, and how many electrons. Atoms of an element are arranged horizontally by increasing the atomic number in rows called periods. So as you move from left to right on the periodic table, the atomic number increases. Atoms are also arranged into vertical columns called groups or families. Atoms in the same column, elements in the same column have similar properties. So all of the elements in the first column are alkali metals, and they have very similar properties. Atoms shown in the periodic table are electrically neutral. That means that they do not have a charge. And so you can also tell the number of electrons in an atom that is neutral by looking at the periodic table. Here we have a very small portion of the periodic table. These are the elements that are most often found in the body. Okay, we have hydrogen, we have carbon, nitrogen, oxygen. Those are the main elements found in our bodies. Some atoms are radioactive. There are isotopes of atoms. That means that they have the same number of protons, but they have a different number of neutrons. And sometimes they don't like having that number of neutrons, and so they will spontaneously break down those neutrons and kick them out. So those are what's called radioactive isotopes. They give off energy in the form of rays and subatomic particles. They can be helpful or harmful depending on what element it is and what isotope it is. Carbon-14 is an example of a radioactive isotope. We use this a lot in history whenever we're trying to date something. We're trying to figure out how old it is. We also use radiation in medical treatments. So cancer treatment is a very popular one. When a person has cancer, they will treat it with radiation, which damages the tumor or the cancer cells and causes them to die. We also use radiation in our food production. We irradiate our fruit, which means we treat them with radiation, and that kills the bacteria and the viruses that are living on those fruits and vegetables, meaning that they last longer. They don't decay as quickly. And that's why the cherry tomatoes that I buy at Walmart will stay fresh for up to 2 weeks, whereas the ones that I pick in my backyard are only good for about 4 or 5 days, because I don't treat them with radiation to kill the bad stuff that lives on the skin of those tomatoes. Electrons and energy. Electrons are attracted to the positively charged nucleus. Thus, it takes energy to hold the electrons in place. And it also takes energy to push them away and keep them in their own shell. The more distant they are from the nucleus, the more energy it takes to hold on to them. Electrons have energy due to their relative position, so it's potential energy, and it's due to their distance from the nucleus. Electrons also determine what behaviors your atom exhibits. The Bohr model is a very useful way to visualize atoms. It's not entirely accurate, but it's a good way for us to visualize what is there. Electrons revolve around the nucleus in the Bohr model, and they are in distinct shells. For atoms with atomic numbers of 20 or less, the following rules apply. The first energy shell can hold up to 2 electrons, and each additional shell can hold up to 8. Each lower shell is filled before the electrons are placed in the next shell. These rules cover most of the biologically significant elements, so this covers all of the elements that we're going to talk about in this class. Valence electrons are electrons found in the outermost energy shell. They are important because they are the ones that actually determine the chemical's properties. Atoms are not happy unless their outer shell is full, and they will do whatever it takes to fill that outer shell. We refer to this as the octet rule because most atoms want to have 8 electrons in their outermost shell. Hydrogen and helium are outliers. They want different numbers because they're so small. And so an atom will do whatever it takes to get 8 electrons in that outermost shell. It will give them away, it will take them, or it will share them with another atom. The number of electrons in an atom's valence shell determines whether it gives them up, accepts them, or shares them. Atoms that have their valence shell filled are chemically stable. That means that they don't like to react. They're happy. Atoms that do not have their valence shell filled will react until they do fill that valence shell. Here we have the Bohr model of hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. These are the atoms. These are the elements that are most common in our bodies.